Also, this is right around 2014 now where we're going to be. So this is when memes were really a big thing, right? So in 2014, 2015, if you were in deep learning, you couldn't do one deep learning conference or one deep learning talk without having memes involved. So just as a nod, I'm putting this meme here that we need to go deeper meme. And this actually influenced a lot the whole deep learning community, and we'll see how. So we're skipping over now to 2014. And 2014, we have the very deep convolutional networks for large-scale image recognition, published by Simonian and Andrew Zisserman. So they were from Oxford. And now, so they inspired themselves from AlexNet and came up with an architecture that performed much better than AlexNet. And you can see already the huge decline. And we're going to skip over 2013. It was a very similar architecture to AlexNet, but suggesting a few improvements. So we're going to go over to 2014 and see what happened then. So, again, we have this idea of depth. So this is a quote directly from the paper. We did not depart from the classical ConvNet architecture of Lequin et al. From 1989, but improved it by substantially increasing the depth of the network. So there's really this idea right now that if you just go deeper, you're going to get better performance. So let's look at the architecture. Again, very similar in structure to what we've seen so far. So we have a series of convolutions, followed by nonlinear activations, some max pooling, and again, this concept of blocks. So here we have 2 convolutions followed by a max pool. This happens again, which is then fed into 3 convolutions followed by a max pool. This happens again another 3 times, followed by some fully convolutional layers. But it's really these same building blocks that are coming over and over. And their main contributions here, first of all, was that they put smaller kernels everywhere. So in the original AlexNet paper, we saw that there were kernels of 11 by 11. And they decided, no, we're going to put 3 by 3s everywhere. And there's a reason why they did that, and we're going to talk about it. And they also added more layers. So in this case, in this specific example, this is called VGG 16. If you do the math, you'll see that there are, in fact, 16 layers total to this model. Another really interesting thing is that the spatial resolution is preserved after every convolution layer. So what that means is when you stay within a block, up until you hit the max pooling, the spatial resolution is always the same. So this is equivalent to doing the same convolution that we saw earlier. And yeah, the downsampling only occurs when they do their max pooling. So in their original paper, they proposed many different configurations of this VGG model. So here we see there's a VGG 11, VGG 13, and the number always indicates the number of layers that were present in the model. So it always starts with an input image, and then what changes is the amount of convolutions and also the depth. So here we see 64, that's the depth. So we have a depth of 64 after our first convolution, a depth of 64 after our second, followed by a max pool, followed by a depth of 128, et cetera, et cetera. And you go down your network until you finally do your fully connected layers and your softmax. Now let's compare this in terms of layers and parameters. So we saw that AlexNet had 8 layers. VGG 16 and 19 had 16 and 19 layers. And the number of parameters you can see is already starting to increase quite a bit. It's already more than double the number of parameters. And we have more than double the number, or more or less double the number of layers. But you can see how there might be a problem with scaling these kinds of models. So first of all, why did they use chains of 3 by 3 convolutions more than a single 7 by 7 convolution? We talked about this earlier. It's the concept of a receptive field. And in their paper, they say, it's easy to see that a stack of 2 3 by 3 conv layers has an effective receptive field of 5 by 5. If you put 3, that's an effective field of 7 by 7. And so the intuition is the following, and we kind of talked about this earlier today. If we take this specific output of our convolution, we see here that it looked at a 3 by 3 window to get one single output here. And by traversing this 3 by 3, this 3 by 3 window now has a receptive field of a 5 by 5 field. And again, if you do another layer on top of that, you're going to get to the 7 by 7. Another layer, you're going to get 9 by 9, etc. So why would they pick the 3 by 3 compared to the 7 by 7, for example? Well, the reasons are twofold. One is you can add nonlinear activations between the two, so that already makes your model more complex. it increases the complexity of your network in terms of the representations it can learn. And another reason is if you do the math, you actually find out that multiple 3x3s to get an effective 7x7 field of view is actually cheaper in terms of parameters than a single 7x7. So by doing these multiple 3x3s, you can go deeper with even less parameters. So that was also one of the motivations behind their design choice.